So last time we talked about the use of generative AI, adversarial network, and we started from the vanilla flavored GAN, which was to generate a synthetic image from a random input, right? Random noise as an input. And then we move on to this question of translating between images. So, yesterday we talked about this pix-to-pix idea where, we prepare a paired data. So if you're interested in, for example, translating from a line sketch to a photorealistic rendering, then you would need a paired images and train GAN accordingly was the idea. Now, if you think about the real, practical applications, this is not so much desirable, in terms of the formulation, because in case of the line drawing, yeah, maybe, you can apply an image filter to a real photograph, and then the image filter will give you this kind of a line drawing. So the edge detection filters and things like that can create this kind of a training data. There's a one-on-one matching. But for more generic scenarios where we do not have the luxury of having a paired data. So for example, for whatever reason, let's say you are interested in converting horses to zebra and zebra to horses. In the pix-to-pix formulation, you would need the horse and zebras standing at the same location, exact same location with the exact same background at an exact same posture, so that there's a pixel-to-pixel correspondence. But in this case, that's not really possible because of the practical reasons. So for those unpaired data sets, so we have a set of images of horses and a set of images of zebras, and then they're not necessarily one-on-one. There's no one-on-one correspondence. So how can we leverage this kind of data set is really the idea of the algorithm that we're trying to explore. So again, since we do not have the input-output pair, the previous formulation of the pix-to-pix is not really, available for this kind of problem. So to this end, Zhu et al. Came up with this idea of cycle-consistent adversarial network, or for short, cycle GAN. The idea of cycle GAN is actually surprisingly simple. So we're considering here a pair of different GANs. Okay, so we're two GANs. So each GAN, we have two neural networks, right? Discriminator and the generator competing against each other. And then we have another pair of discriminator and generator, okay? And, oops. Even PowerPoint knows it's Friday. So we have two GANs. And what happens here is that, in terms of the notation, we're going to call, all the horses an X, set X. And then we call all the zebras set Y. And then the two generators work in both ways. Why is it moving automatically? Works in both ways. So you can consider a generator that generates a zebra image from horses, right? So that's one generator. And then there's another generator that generates horses from zebras, okay? And what we're going to do is to define a loss function called a cycle consistency loss. The idea of cycle consistency loss is that, you start from a zebra generator. So you start from a horse. Using the zebra generator, you generate zebra. And then from that zebra image that is generated by, from the horse image, we apply the horse generator, which is the function f, to generate the horse image again. And if both the zebra generator and the horse generator does its job, then, if you go back and forth, when you come back here, the horse image generated by this process should be the same as the original image. So mathematically speaking, you start from a set X, map it to set Y, and then come back to set X. The discrepancy between the reconstruction is what's defined as a cycle consistency loss. Of course, you can go the other way around. So you start from zebra this time, use a horse generator to generate horse images, and then go back to the zebra image. And then again, you start from the set Y to set X, and then come back to set Y, and then you measure the difference between the two. So that's the reconstruction error defined as the cycle consistency loss. So on top of the GAN loss, you add the cycle consistency loss, and then you train, the two generators together, two GANs together. And as a result of that, you can achieve something like this. So as you can see here, the exact same horse. Now we have a stripe pattern. Of course, this is a frame by frame generation, so it's not a video generation algorithm. So for each individual frame, independent from other frames, we're generating the zebra pattern from the horse image. So when we play this as a video, you can see a little bit of fluctuation of the the stripe pattern, but other than that, it looks pretty realistic. Of course, here's actually a funny failure case of the cycle GAN algorithm. So we have a guy sitting on a horse, and if you apply cycle GAN, this is kind of what you get. The reason is because, in this particular model, the ImageNet database was used for ImageNet database. There's a class named Wild Horse, and then there's also a class named Zebra, and then you can extract, lots of images of zebra and lots of images of wild horse, and then train cycle GAN to make the conversion between the horse and zebra. But then in that particular class of wild horse, there was no human at all in the training data set. So the model, which has never seen humans with the animal, doesn't, is unable to distinguish the human body from the horse. So this is a really funny, failure case. But the cycle GAN, trained in this manner can help a lot of engineering applications. So here's one of the very recent publications in the Journal of in the Journal of Chemistry Letters. What's happening over here is a conversion between two modalities of molecular images. So we have the microscope image on the left, and then on the right, we have the synthetic molecular structure generated using cycle GAN. So as your electron microscope scans through a chemical structure, a microstructure, cycle GAN can be used to generate a corresponding molecular images that correspond to the microstructure image. And the authors present a way to automate the process of experiment and measurement using algorithms like cycle GAN. So this is kind of automatic data analysis framework, where again the cycle GAN is trained on an unpaired set of images. So on one side, instead of horses now, we have microscopic images. And then on the other hand, instead of zebras, we have the molecular drawings. And then, based off of the cycle consistency training, now the cycle GAN is able to convert, from molecular structure to an STM, microscope data, or vice versa. You can go from the microscopic image to the molecular structure drawing. A data analysis in experiment is kind of the idea here. Style GAN is another variant of GAN that we already kind of briefly mentioned when we were talking about Park. Again, we have lots of synthetic images of people, and they're all, fake. They're all fake imagery. The idea of style GAN, we have the usual GAN, as you can see over here. We start from a random noise, and that random noise will be, convolved and, blah, blah, blah. And then at the end, this network will generate a synthetic image like the ones over there. Now, the unique idea of style GAN is what's called a style vector. And this style vector is actually the one that intentionally bias the generative process of GAN. So every now and then, this style vector sort of hijacks the intermediate throughput of the neural network. So, convolution layers will generate some, feature distribution, right? And then the whole idea of, generative adversarial network is to let the convolutional neural network the real. But during that process, check the information, and then intentionally, add the number, distribution to the RAM. That what we're able to do to enforce certain style, so that with that bias, we can, for example, change the tone of the gender. We can change the wearing of glasses. We can change a lot overall visual structure of the individual. So here, the really paper is this thing called the adaptive input normalization, or ADA-in. The adaptive input normalization layer works in a way that, whatever convolutional neural network, whatever a previous convolution layer, we Z-score at, convolution. Of a bias factor, the shift factor, offset factor. Factors are learned style vector. So the style term is the offset term, learned from data. So you can see over here, we have different styles of, different individuals. So we have source A and source B, and then, in between, we have the blending of those, different individuals. So if you mix, this lady over here with this lady, this is what you get. That they sort of inherit, of each other. Kind of, or, like, this black woman over here, combined with this little child, right? And then as a result, we have something in between, right? That inherits the skin tone and, things like that. So this is you can learn, use it to manipulate the generated images. So again, in terms of the engineering applications, the style vectors can define, different material species. So let's say you have certain, copper alloy, and then, certain other alloy. And then, you want to train a neural network to generate synthetic images of those, alloys. And depending on the whole, composition, the microstructure images will have different styles, right? And then the style vector obviously is something that can, allow you to, bridge, different styles across different compounds and different alloys, and so on and so forth. I just brought this video because I thought this was brilliant. Jeff Bezos, the former CEO of Amazon, and Elon Musk. So it's pretty realistic. The fact that this is already several years ago, and in terms of the technology, this is already outdated technology, but we already have a pretty good result. So I thought I would just show this. So, like I said, the style again. I mentioned that the idea of style vector can actually be very useful in solving a lot of engineering applications. So we already saw this application of the style vector inside of Park, so that we can kind of bias the prediction using the style vector. So I'm going to just skip through because you already saw. For the overview of generative adversarial networks, or GAN. Unfortunately, the world of deep learning changes really fast. So GANs are now a little bit outdated. Nowadays, everything is diffusion modeling. So this session is going to be about diffusion models. So things like OpenAI DALL-E, you probably know this already. Now, it's available in ChatGPT as well. So you can, give a text prompt, and then, given the text prompt, DALL-E will generate a synthetic image. So, not only the models nowadays are able to generate a synthetic image out of, some random seed input, the models are now able to connect the dots between, the text data versus image data. So if you look at the generated images, they're all very, text prompt very well. Image gen is the diffusion algorithm can, again, so Gemini, for example, uses this algorithm to generate a synthetic image. This one is a little more, I guess, advanced. Will have more functionality in the sense that it can also generate video. So again, see that, from text prompt, you can actually generate videos like these. And they all kind of look realistic, although, if you look at them carefully, you probably be able to spot some awkward subtleties. But still, Asia, the future models, pretty impressive. Another generative AI algorithm, and this is something that you can use to edit, basically Photoshop an existing photograph into something else by using text prompts. So in Photoshop, it's an excellent tool, but you also need to have your own skills to manipulate images. Versus with this one, you can just type a text prompt, and then given the text prompt, it'll like over there we have the word, and then from this as a result of that, it spread or it could go.